I've developed this habit of giving talks that deal with estimating data reduction. And people might ask, well, is he doing it again? And the answer is yes. I am doing it again. And I'll admit, not only am I doing it again, like the core technology or the core algorithmic methodology we'll be using in this talk today is pretty much the same as we've used before. There are variations, but not dramatic. So it's more or less the same techniques. What has changed is the problem. We're asking a different problem. It's a different use case. So let me explain. In previous works, we had this big pile of data that was not reduced. It was not compressed. It was not deduplicated. And you want to look at this, and you have this nice, neat storage system that does compression, does deduplication, and you want to turn it on for this data, or you want to migrate it into the system. And now you ask, OK, how much space will it take on this system after being deduplicated and compressed? So that was a question we were dealing with before. The question now has changed because in this work, there's no longer this big pile of data outside of the system. This data is already inside the system. It has been reduced. It has been compressed. It has been deduplicated. So basically, we know everything about the data reduction of this data, or the system knows everything, right? Well, not quite. And the not quite is, it's a tricky thing. The system knows, or most of the systems that do this, what they do know very well is how much capacity the entire system is storing, how much physical capacity is being used. But storage is not managed at the granularity of the entire system. It's managed rather at a granularity which is much smaller. It's a volume, it's a pool, a group, a file. In this talk, I'll be talking volumes, but it could be general. And you need to report capacities. In order to make decisions, you want to report capacities at the same granularity that you actually do operations, management operations. OK, so we want to report at the volume level, not at the entire system level. So why isn't this working at the volume level? And the answer is deduplication happened. Deduplication changed the picture. So what happened with deduplication? Prior to deduplication, each volume, for the most part, there's snapshots and stuff, but for the most part, each volume was the owner of its own data. Even if it compresses, it's still the data belonging to this volume. So the physical capacity was related to a specific volume. With deduplication, world looks very different. So there's a big mess there where data is being shared between various volumes. So who is the owner of the data? And basically, the data reduction of a volume is no longer dependent on the data of the volume. It's dependent on the data of the volume and all of the other data in the system. So it's a much more complex problem. What are we doing in this work? We are trying to estimate number of statistics measures for each volume or group in the system. These are the metrics we're trying to find. So reclaimable capacity. Reclaimable is how much space would I free if I remove this volume from the system. Now, with deduplication, this could be 0, because if the data is shared with other systems, it doesn't matter how large the volume is. You're not saving any physical space. So this is really a crucial measure that needs to be known in order to move things out. Now, when you move things out, you're moving them typically to another system. So there's another question. How much capacity would this volume take on another system? We're trying to answer that as well. There's another parameter. We're calling this attributed capacity. So attributed capacity is how much we said there's no volume owning the data, but what is the respective physical capacity a volume is owning? And let's talk about a fair sharing here between volumes. So 2 volumes share data. Let's split it half and half. That's attributed capacity. We're also looking at a breakdown. How much are you saving from compression? How much are you saving from deduplication? All these are unknown in current systems. And people making decisions are working in the blind with respect to these. So I want to claim that I'll give you some motivation. If we had these, we could do a lot of different things. Some motivation, you can go and read a nice position paper at Hot Storage 2016 by Phil Shalane et al. They said, here's some neat deduplication problems that we need to tackle that nobody is studying. And here, we're actually addressing a lot of these. So 3 of them: understanding capacities, storage management, even at a large scale of a data center, optimizing capacity across systems, and then tenant chargeback. We want to build tenants fairly, not according to the logical capacity they are using, but according to the physical capacity they are using. Okay, so that's motivation. Why is this so hard? It's hard. Well, the first thing to notice is the system knows all the information it needs. It has all the metadata to make sense and compute all the measures that I mentioned. But that's a lot of metadata. We're talking about a lot of data, and it's just too much data to compute. You can simulate that, but it's just too intensive. I'll show numbers soon of how much this actually is. That's one problem. But you can try and do all sorts of tricks that are typically done in accounting. For example, one trick which is typically done is every I/O, you just account it to the volume which it belongs to, and update the stat for that volume. But that can't be done here because each I/O can affect all of the volumes in the system potentially. Another problem, let's talk about the reclaimable capacity. It's not additive. So you cannot compute the reclaimable for volume A and volume B, and now from this deduce what is the reclaimable of the group containing both of them. So if I remove 2 volumes together, I need a whole new computation in order to get this. Now I'll mention since reclaimable is so important, there are some heuristics to dealing with this. There are solutions, but they suffer from 2 main problems. One, they don't work for groups. And the other is they can be grossly inaccurate. And grossly inaccurate meaning all the way inaccurate. It says you're freeing 0 and you're freeing 10 terabytes or whatever. That's grossly inaccurate. So we want something that actually works and actually gives guarantees. Okay, so our solution. Volume sketches. And I'll say just a word about sketches. Sketches are techniques that come from the realm of streaming algorithms. And basically, a sketch it's like a sketch in drawing. What we're trying to do is capture very little information about the system, as little as we can, but still not lose the essence of what we're trying to see. Okay, so we're trying to compute these metrics about capacity. We want minimal information that will give us good estimates on what's happening there. That's a sketch. We are using what is called content-aware sampling for actually creating the sketches. The methods we are using, specifically the closest one, there are a list here of some that are from the world of streaming, from estimating distinct elements. They were also used in deduplication. And we do need to do some changes and tweaks. They don't work as is. So we had to work some, which is nice because then the work is more interesting. You feel better about it. Okay, the actual method. So a word of just a preliminary deduplication is done in chunks. Data is going to be broken into chunks, could be fixed size, variable chunks, but think about 8 kilobyte chunks. For each one of these, you compute a fingerprint, and the fingerprint is a unique identifier. It's a random cryptographic hash of the data in this chunk. And we already have these fingerprints in the system because that's the method that is typically used for finding the duplicates in a system. So we have these hash values. Now think of these. These are strings of bits, 160 bits, 256 bits, what have you. The method is this. Does your hash begin with 13 0 bits, not bytes? Does it begin with 13 zeros? 13 is a parameter, of course. If yes, it's in the sketch. Keep something about this chunk. If no, just ignore it, forget about it, and go ahead. What this means is that the sketch is looking at a fraction that, on average, it's 1 over 8,000 of the data in the system. If we do the math, the sketch size is smaller than the written data by a factor of 3.5 million. And now it's manageable. Now we can actually do analysis on it because it's become not big data. It's reasonably sized data. How does this look in terms? Here's an example. If I have 1 petabyte of data in the system, a typical storage system doing deduplication will hold on the order of 10 terabytes of metadata. Now, analyzing 10 terabytes of metadata is way too hard. But the sketch is going to be 300 megabytes. And 300 megabytes is manageable. OK, some notes on the sketch. So one, why does it work? And it works because of one crucial property. Every hash that is in the sketch, we are monitoring all of the appearances of this hash in the entire system, in the entire petabyte or what have you. That's a crucial property. That's just intuition why it works. Another point, what do you actually do with it? So the method is very simple. To estimate the capacity measure that we're trying to estimate, simply estimate it on the sketch, as if the sketch is the entire world. And at the end, multiply by the sketch factor. Bring it back up. That's the estimation. Now, it gets a bit tricky when you're trying to do this for reclaimable, for et cetera. You need to involve the whole notion of a volume in it. But just to give you a sense, I'm going to show some formulas. Don't be afraid. It's going to go over quickly. This is the computation for the pile that is outside of the system. In order to do our computations, we have to work a bit more. We have to add parameters that are relevant to a volume. There's the reference count per volume, reference count per system. This is the attributed, and this is the reclaimable. So it looks, you see, we're adding up some more work. I told you it'll be quick. So if you want to really dive into these, you can go to the paper or look me up after that. Now, the complications also come with the fact that we actually need to now prove that we have the accuracy working for all of these variations that we put in. So what can we say about the accuracy? Well, great. We have a theorem with actually an accuracy statement, a bit of an intimidating theorem, but don't be intimidated. I'll jump over that as well. Basically, I'm going to tell you that the bottom line is this. The accuracy is just a pure function, a complicated function, but a function of the physical capacity we are trying to estimate. So if the physical capacity is large, we get better accuracy. It looks like this. So look at the graph. If we're trying to estimate for 1 terabyte, for example, the x-axis is gigabytes, then the skew in percent is around 2%, maybe less than that. If you're trying to estimate for 50 gigabytes, you don't get such a nice skew in percentage, but it's still meaningful information. And the fact that we can actually give you an accuracy bound or how much we think this estimation is tight is really crucial, because now you can look at the number and say, OK, is this helpful for me or not? Is this estimation good enough? So it's critical that we have this. We showed that it works for all the estimations that we have. And we had to work for this, too. It's a Chernoff bound, but we have to mess around with it a bit. OK, enough theory. Now let's talk about deployment. we took a different design than what we could have. The design said we're going to analyze the sketches outside of a storage system. So rather than computing them on the storage system, we're avoiding putting extra CPU cycles on the system. We're doing their computations outside. It's easier to deploy, and it's also very good if you want to do cross-system stuff. Now, the sketch collection itself, well, it's in the machine. We have this design where all the sketch is in RAM always. So when you're pulling for sketch data, you're never adding I/O to the system. The machine, its whole purpose is providing high I/Os. So we don't want to harm that. And this is a real work. It is deployed in a real all-flash system. It's the IBM flash system A9000. So it's already in the product. Just one note, because we're doing this in a highly distributed system, basically the sketch that we're seeing is not a snapshot in time. It's something that is sort of a fuzzy point in time. But since we're doing estimations, this is good enough. If the system does not change drastically in a few minutes, then you're fine with that. OK, the analysis, it runs in 2 phases. First, we ingest the data, aggregate it into volumes, et cetera, make sense out of that. And then analyze it, meaning compute all the reclaimable, attributed, et cetera. In our implementation, we really emphasize speed of the second phase because we want to be able to answer queries very quickly. Because think of cross-system optimizations. Now we want to do enumerations on many options. We need this second phase to be very fast. OK, evaluation. Evaluation we did on 3 types of data. There's synthetic data. There's the beautiful traces from the work of Meyer and Bolosky, deduplication traces that are available on the SNIA website. And we also have some call-home information statistics from the field giving us general statistics. I'm showing some examples on timing. It's in the yellow. 89 seconds to digest on a system that has 1.5 petabyte of data. So that's a lot of data to digest there. We always work here under 2 minutes, which is reasonable. The analysis phase, again, is much, much faster. And if you're analyzing, you're questioning a specific group, we're way under 1/10 of a second and much faster than that. Evaluation of accuracy. I always like a nice bell-shaped histogram. So we got that. What I'm showing you here is 768 volumes in the UBC set. We did the estimation for the reclaimable for all of them, and we normalized it by the accuracy guarantee. And what you can see is that with overwhelming probability, we're within 50% of the guarantee. In some cases, we got up to 80% of the guarantee. We're always well within the guarantee. So the guarantee really works, and we got a nice bell shape. Finally, data center optimizations. I said that it's really useful for this use case. And to exemplify this, we went and wrote a greedy algorithm that tries to do something in this realm of multi-systems. And here's the setting. We took, again, we evaluated this on the UBC data set. We took all of the volumes, 760, and divided them into 4 random groups. And said, OK, we have 4 systems here. Each one, on average, has on the order of 7 terabytes of data. And the goal was this. We're asking the algorithm to find a plan to free 1 terabyte from one of these systems. So we have a source system, and we're saying we need to free 1 terabyte of physical capacity from this system. Please generate a plan for us. And the plan is supposed to say, OK, which volumes should you take out of the one system? And where do you want to move them to? And there's an overall objective here. We want to reduce the overall capacity in the entire data center. So results on this, the algorithm ran between 30 seconds to 55 seconds, so it was fairly fast, and it came up with a plan where it removes 1 terabyte from one system, and it takes up less than 750 gigabytes on the other system. So there was nice savings here. This is, I mean, you can always generate data sets synthetically that will give you more or give you less. This is real data. We didn't know what to expect. I think this is pretty nice saving, larger than we expected. So basically, that's it. As a summary, I'll say we're introducing a method to deal with data inside a deduplicated system, really bring clarity to measures that have to do with capacity. And I think it's just the beginning, because this is a tool that opens up options for much smarter things that can be done with capacity, with data reduction. And yeah, and it's deployed in system, which is great. Thank you.
Hi, nice work. Hello?
Yeah.
So just wondering a simple question. How do you settle down on the parameter to 13? Do you from the accuracy using the theorem to derive, or using some experiment? So
it's a good question. It's a trade-off here, because the higher the number, the smaller the sketch is. On the other hand, you get less accuracy. So we tried to find a medium that is manageable in terms of the RAM that we're willing to invest in the system, and is accurate enough for the purposes we saw. We ended up with 13. It wasn't really a methodological way. We just felt this was the right trade-off, and we stuck there.
OK, thank you.
Following up on that, what's the sensitivity to the number of bits you use if you change it to 12 or 14?
Sensitivity in terms of the amount of data in the sketch is just clear. It's double or half. Sensitivity with regards to accuracy is not very dramatic. Or I had that graph. You can see it kind of falls. Basically, I think that if we could have gone down, and it's kind of the barrier was the small volumes of around 50 gigabytes. You couldn't have any decent accuracy for them if you would have gone lower than that. But it's really a game. You can just look at this graph and say, OK, what happens if I reduce the amount by half? Then capacity is basically halving. Then the accuracy for 50 gigabytes is now the same accuracy you would have gotten for 100 gigabytes in another test.
OK, any other questions?
Glenn Watkins, HPE. So along those same lines, would the number of bits change per chunk if it was a variable size chunk, right?
And no, I don't think so. I wouldn't have changed that. The variable size chunk is just, on average, it's going to give you the same. I mean, it depends what is the average size of a chunk. If the average size of a variable size chunk is on the order of 8 kilobytes, then why move from it? So it all averages out.
OK, let's thank Danny.
Thank you.